My name is Ashwin Geddesa, and I'll be presenting my thesis work on expanding the training data for neural network-based hate speech classification. I'm the final year of my PhD, and I'll be defending on 6th of May. So this thesis has been supervised by Irina Elena and Dominic Faure. Irina is on Zoom, and Dominic is right next to me, and also co-supervised by Dietrich Klacko, who works at Saarland University. We have been funded by the project, the French government and the German government, ANR and DFG, under the project Migration and Patterns of Hate Speech in Social Media. We call it Emphasis. Uh, so the worry of this presentation goes like this. We introduce the problem and then we talk about the various solutions that we have addressed. We have looked at 3 different solutions to improve hate speech classification. They're based on semi-supervised learning, data augmentation, and multi-corpus learning. And then we'll give a conclusion and also the direction for the future research.
Ashwin, speaking of questions, if anybody has questions, when is a good time to ask? Just as the questions arise, or at some stop, or at the end?
So I think like people can note down the slide number and I can answer everything at the end. That would be better.
Okay, perfect. So we have question and answers. We have chat for the questions. So please accumulate your questions with slide number, and Ashwin will answer that at the end. Thank you. Please go on.
Thank you. So let's begin with the introduction. We know that there are more and more internet users, and it's increasing day by day. And with this, there is also increase in hate speech that's circulating online. And hate speech especially targets the minority section of the society. It can be based on various societal phenomena such as religion, gender, ethnicity, and other factors. So what leads to the problem is hate speech also leads to threat violence and other intolerance in the society. If you look at the examples of hate speech, only lesbians get their nips pierced. We have targeting to the gender identity. You are an illegal immigrant and don't belong in this country. So it's targeting at the immigrants who are again minority of the society. So these are the reasons why we need to curb the hate speech. And to curb the hate speech, currently there is manual moderation where human operator looks at the data and filters the data. But this is time consuming and expensive. The more number of users, more is the cost involved. Thus, we have to find a suitable technique to quickly remove the contents, which can be done through automatic classification by using machine learning or NLP techniques. There are various challenges involved in hate speech classification. The first thing goes with the varying definition of hate speech. There is no one fixed or finite definition for hate speech, and different organizations have different definition for hate speech. For example, the definition of hate speech by Twitter and Facebook are different. Then the next problem is implicit and explicit hate speech. Explicit hate speech is where the hate speech is expressed through certain profane words. For example, this guy is the biggest faggot. Oh my fucking god! So the word faggot or MFG, which explicitly mentions the hate terms forms explicit hate speech. While you can also convey hate speech through sarcasm or irony. And that becomes implicit hate speech. For example, those guys are the definition of white trash. So none of the words here are profane, but still it's hate speech. And then there is problems with the corpus. That is, corpus based on the way it is sampled, the way the data is collected, it can have bias. So bias leads to the generalizability problems when a model trained on one data set is tested on the different data set. And the next problem is hate speech data sets do have very few amount of labeled data in it. The third problem is class imbalance. It's something got to do with the classification, but class imbalance is you don't have equal amount of data in all the classes. This can be naturally because hate speech occurs very few on the internet, and the other one is based on the sampling strategy. You can still have some imbalance in the class and different labeling schemes. So uh, when the data set is annotated, different authors use different annotation schemes. Some people go with simple annotation schemes, such as just labeling it as hate speech or non-hate speech, or some may want more precise ones, like they want to distinguish between abusive speech and hate speech, where they create three-class classification, like normal speech, abusive, and hate speech. Or it can be based on very particular phenomena of hate, such as racism or sexism, and then you have none of them. So uh, neither. So it can have again three or more classes like that. And then influence of context. For example, if we look back at this example, those guys are definition of white trash. Uh, we know that the word white is referring to ethnicity, and trash kind of refers to the hate against those people. But without knowing certain context, it's hard for us to say whether it's hate speech or not. And this is problem for both humans as well as machines. So the objective, what we try to look in this thesis or in our work. So primarily to employ neural network based hate speech classification, uh, deep learning, that is neural network or deep learning based classification. These have outperformed classical machine learning based techniques. But then these methods, that's deep learning based methods, depend on quantity of data. They need more data to improve the model performance. More higher the data, better is the model performance. But then we know that hate speech data sets have very small amount of data within them. So we primarily looked at improving the classification performance by increasing the amount of training data. Uh, the data sets that we have considered in this thesis, we have looked at 5 data sets. Uh, 4 of them have been sampled from Twitter, and the author names have been used as the name of the data set here, except for HateEval, which comes as a part of HateEval challenge. And we can observe that there are different labeling schemes. For example, Davidson and Founta are three-class classification, where there is fine-grained distinction between abusive and hateful. And HateEval and Wasim, they have non-hateful and hateful. While Wikipedia has different labeling scheme, they use toxic versus non-toxic, where toxic generally encompasses abusive and hateful. Overall, we see that we have less data. They occur in few thousand samples. And when we look at hate speech, hateful category, we just have 6% in Davidson and Founta, which clearly shows an indication of class imbalance in the data sets. So, to increase the amount of data, we primarily focused on 3 research questions. So how can we efficiently combine unlabeled data along with the labeled data? This is because there is a lot of unlabeled data out there which has not been annotated. So can we combine them with the labeled data to improve the classification? And the next question we try to answer is, we just have the training data. So can we generate more training data by using just the original training data? And the third question is, well, with the increase in the focus of research towards hate speech classification, there are a lot of data sets, but they differ. But can we combine them together to have increased number of samples to train a better model? So these are the 3 research questions that we try to answer in this thesis. So moving on to the next chapter, that's semi-supervised learning, which is our first method for one of our research question. So the research question that we are trying to answer here is how to efficiently combine the unlabeled data along with the labeled training data. So we do that using semi-supervised learning. Uh, in reality, we have a small amount of labeled data and abundant quantity of unlabeled data. And semi-supervised learning combines the labeled and unlabeled data together while training a system. The algorithm that we looked at was a graph-based algorithm called label propagation, which propagates labels from labeled data to the unlabeled data. And it is based on the nearest neighbors. That is, an unlabeled data gets its label based on who its neighbors are. So how do we represent these data? So for the label propagation algorithm relies on the representation of the data, by which we mean that for a very good performance of label propagation algorithm, the representation should be such that the samples that have similar labels should be close to each other in the representation space. Uh, so, so how can we go about with this? So one such representation is pre-trained embeddings. We have pre-trained sentence embeddings that represents entire sentence. One such example is universal sentence encoder that we use. And so, so how are the data samples represented in this representation? So the samples which are semantically similar are close to each other in the representation space. That's if we look at the cosine similarity, the samples that are similar to each other should be close to each other. Uh, we looked at two scenarios for our experimental experiments. One is we consider that unlabeled data comes from the same distribution. So how do we achieve this? For an entire data set, we split into three parts. That's training set, development set, and test set. What we do is within the training set, we split into two parts. That's we considered 20% of the training set as the label set, and the rest 80% as the unlabeled set. So there it's split in the ratio of 1:4. And then we also look at what happens when the amount of labeled data reduces. That's how well our algorithm performs when we have less amount of data, for which we reduce the quantity of label set to its 100%, 75%, 50%, and so on until 5%. But the main challenge goes like this. Uh, in reality, we always have data coming from different distribution. The data is not exactly like what you have in your original data set. So how well does it perform when you take the real unlabeled data? So we look at the factor of how well the algorithm performs when we have unlabeled data from entirely different distribution, for which we took a data set by Stanford. They have provided a Twitter dump of billions of tweets. But what we try to do is we take the same number of samples that we used in the previous experiment as our unlabeled data. So we look at two different scenarios in this experiments. So for our approach, for the classification, we have used multi-layer perceptron. This is because use embeddings are a single vector representation of of dimension phi 12, and we want to so we cannot use models such as CNN or LSTMs when we have a single vector. Uh, so for our baseline, we just look at how well the multi-layer perceptron performs only on the labeled data. That's we're not looking at the semi-supervised learning. And the next approach, so this is using the semi-supervised learning, wherein we have used pre-trained representation. So so what we do is we first obtain the use embeddings for our labeled and unlabeled data, and we pass the labeled and unlabeled data through our label propagation algorithm. And now uh, the label propagation algorithm provides the labels for these unlabeled data. So now we have labeled data and unlabeled data along with the labels obtained from label propagation algorithm. So with this, we have labels for both labeled and unlabeled data, which we combine and use it for use to train our multi-layer perceptron classifier. So the input to multi-layer perceptron will still be use embeddings itself, use embeddings of both labeled and unlabeled data. Uh, this is our uh, uh, this is our semi-supervised approach. So what happens to the results? So basically we have baseline, which is indicated by blue line, and green line, which represents semi-supervised learning using pre-trained representation. On the y-axis, we have our model performance indicated with macro average F1. Higher the numbers, better is the results. And then on the x-axis, we have percentage of the label data. What we observe is when we use the pre-trained representation, we have a significant reduction in the model performance. So why did this occur? We tried looking at the PCA plots of the PCA plots of the labeled and unlabeled data together. So the PCA plots have in red and orange, we have labeled and unlabeled data for normal speech. For green, we have green and cyan, we have green, we have abusive speech, and blue and cyan, we have hateful speech. We do see there is a lot of overlap. That's samples are not separated. But then our original intuition was that label propagation requires data that's already kind of requires representations such that samples belonging to similar class or same class should be close to each other. But in this case, there's a lot of overlap, and most of the samples from the same class are not well separated. So with this, we see that pre-trained representation, although kind of shows that semantically similar sentences are close to each other, it does not model any characteristics of the class label. So what did we try to do? So we kind of try to transform the representation from pre-trained representation to task-specific representation. So the task-specific representations are intended to hold some information about the class labels. So how did we achieve this? We used the same MLP, which was trained on the label data. So our MLP had 2 hidden layers and the softmax classifier. So we passed in the inputs of both labeled and unlabeled data. The use embeddings, which is the input for MLP. The activations from the hidden layer, the first hidden layer or the second hidden layer, we call it H1 representation or H2 representations. So these are considered to be task-specific representations because the model here, MLP model, is already trained on the label data. So it does contain some class-specific information, which it can use to transform the pre-trained or generic representation to task-specific representation. Then the architecture remains similar. Instead of use embeddings, we have used H1 or H2, that's task-specific representation for our label propagation algorithm. And the labels obtained from the label for the unlabeled data from label propagation is then used along with labeled and unlabeled data to train the MLP classifier. So what has changed is the way we have represented the data, so that the way the label propagation algorithm looks at labeling data differs here. So coming down to the results, the new results, which is semi-supervised learning, where input representation for label propagation algorithm is the transformed or task-specific representation indicated in the red line. We do observe that the model performs much better than the baseline that's using only the label data. And also when we have less amount of data, we really have significant improvement in the performance. It's higher improvements as seen when the amount of samples is low. So by this, we can say task-specific representation or the transformed representation are helpful for label propagation, and semi-supervised learning for hate speech classification works well, especially in the low resource scenarios. Also, we tried looking at the representations, the task-specific representations, the transformed representation. We see that now the samples that belong to the same class are close to each other, and the overlap has significantly reduced. And then we look at how well does the algorithm perform or the method perform when the data comes from a different distribution, or when the data is not exactly or very similar to the original training corpus. This is where we have taken the data from the external Twitter DOM, and we still do observe improvements in the model performance when we take the task-specific representation for semi-supervised learning. Uh, so, so in conclusion, for label propagation for semi-supervised learning, we saw that label propagation using the transformed representation performed much better than pre-trained representation, and it also helped to improve the performance, the model performance, and significant performance improvements have been observed in low resource scenarios. And our approach also gives improvements when the labeled and unlabeled data come from different distributions. Moving on to the next chapter, our next approach, that's data augmentation. So we try to answer the research question, how to generate new training data from the original training data. So our solution for this is data augmentation. So data augmentation, it considers few labeled samples and and then tries to generate new data from the original training data, and thus increases few number of samples to huge number of samples. Few of the methods in the literature are replacing words with synonyms. So uh, you have a sentence, you take particular words, you replace with the synonyms. And the next technique, for example, is back translation. You translate from one source language to another. For example, you translate a sentence from English to Russian and back from Russian to English. The same message can be conveyed in a slightly different way, preserving its meaning. So that's how back translation works. And the final technique, which is quite common these days, is data generation using language model. And in our approach, we have tried to use this method. So you train a language model and you completely generate new data out of it. So now, because the model is trained on your original training data, you expect that the generated data should resemble uh, or should be very close to your original training data. Our approach is mainly based on the authors Wulack, and I'll try to explain how they perform data augmentation. So they used GPT-2 model based data generation. So their method goes like this. For example, if you have three classes, they train three different GPT-2 models, one model for each class. So that's they find on GPT-2 models. And then a huge quantity of data is generated for that particular class. For example, the normal speech is trained, the original normal speech data is used to fine tune one GPT-2 model, from which huge number of normal speech samples are generated. Once the huge number of samples are generated, they want to pick the high quality samples. So what they do is they use a filtering technique, which is based on the BERT model. So here, the BERT model is fine-tuned on the original training data itself. And then the fine-tuned model is used to perform classification. And the samples that are high quality will have high softmax scores, and these samples are ranked according to the softmax score, and the top samples are taken and augmented along with the original training data uh, to have increased amount of training data, and then a classifier is trained. So the classifier that's trained as CGRU, they have used CGRU for the final classification. So the drawback of this method is when you have very small amount of data, especially for classes such as hate speech, uh, you really have very few amount of samples to train the GPT-2 model, which may also lead to the model overfitting and uh, such kind of or model under training. So what did we try to change? Instead of using three different GPT-2 models, we try to reduce it to a single GPT-2 model. So we use all the samples of all the three classes together to train a single GPT-2 model. And then we use so this has been done with the objective of conditional language modeling. And then we use the conditional codes to generate data for a particular class. And thus we generate data for all the three classes, huge amount of data for all the three classes. So essentially, our approach is very similar to what has been done before by ULAC, but then the first block has changed. That's instead of using three GPT-2 models, we have used single one. And it also makes sense because GPT-2 model has huge number of model parameters. That's 774 million parameters. So instead of three models with such huge number of parameters, you can just go with a single model. Coming to the setup, uh, so the GPT-2 model that we have used is GPT-2 large, and we have so while generating the data, we have generated 600,000 samples per class, and then we have fine-tuned. So for BERT, we have used BERT based uncased, which is fine-tuned on the original training data, and the top few samples or top n samples have been selected from that. The classification model is convolutional GRU, which combines the convolution layer and GRU layer. So it looks at both the patterns as well as the sequence. That's the objective. Uh, so coming to the results. So we look at the influence of quantity of data. So with this, we try to look at how much data is required to be augmented to see an improvement, or to see what level of performance gain can be achieved by what quantity of data. So we try to look at two things. One is augmenting data to to every class or each class of the each class label samples. So we augment equal number of samples for all the three classes. Or the second thing that second second experiment that we looked at is augmenting only to the hateful class. This is done because hate speech was minority in the Davidson and Founta data sets, and we try to look at if the performance improves by augmenting only to the minority class. So these are the reasons why we looked at two approaches. And what we observe is on Davidson dataset is that with increase in the amount of augmented data, we observe an increase in the performance of the classification. Uh, and likewise, we also see an improvement in the performance when we have augmented only to the hateful class. That's by this we can say by augmenting only to the minority class as well, we do observe some level of improvements. But then the performance that we have observed by augmenting to all the classes is much higher. With this, from this we have seen an improvement from 68.7, which is indicated by gray line, up to 75.4, where we have augmented 200,000 samples for each class. So which is relatively close to 9%. With this, we can say data augmentation helps. Then we looked at what is the quality of data. We try to look at it from the classification perspective. We try to so for this, instead of the original training data, we just took the generated data and then which is then filtered by BERT, and we then train a classifier with only the generated data. We do not use the original training data. So as a baseline results for Davidson dataset, we had a performance of 68.7. But then when we used 500, when we used 25,000 samples for each class, uh, we had a performance of 69.9, which is slightly higher than its baseline. And also when we went with higher number of samples, we observed an increase in the model performance. So with this, we can say that the generated data resembled or had characteristics of original data, due to which uh, uh, the model gave very good performance when it was trained only with the generated data and without any original data. Then we look at the influence of filtering. So whether filtering with BERT was useful or not. So how did we try to look at? So originally we were considering the top n samples, or the top samples which were filtered or sorted by BERT. Instead of this, we try to take the samples which were randomly selected from the generated set, and then we augment it to the training set. So with this, we looked at three variations. That's augmenting 5,000 samples to each class, or 25,000 or 50,000 samples to each class. Uh, in all the three scenarios, we observe a similar or an improved results when the top few samples were chosen. So by this, we can say filtering with BERT was useful. Also, while looking at what exactly filtering does. So we try to project on a PC plot. We try to project the BERT embeddings of original data and the generated data. So because the BERT model is already trained, uh, sorry, yeah, because the BERT model is trained, we have kind of separation. And it's a problem of hate speech, where hate speech overlaps a lot with the abusive speech when it contains profane words. And then when we look at generated data, we do see few amount of generated data of different class. For example, normal speech class overlapping with the hateful class in the representation space. So this is when we have taken the data randomly. But then when we take the top 50,000 samples filtered by BERT, and when we try to project, we observe that the generated data occurs near the centroid of the target class, and there is no overlap. And by this, we also see that the top few samples strongly represents a target class, which for which we want to augment the data. So thus we can say this simple analysis shows that filtering with BERT is helpful. Overall, so concluding this chapter, by data augmentation, so we perform data augmentation using uh, conditional language modeling, where a generative model was used to generate huge amount of data, and this improved the classification performance. Augmenting data generated by conditional language modeling improved the performance, and the performance of the classifier improved with increase in the amount of augmented data. Improved with the quantity of data, and the generated data represented the characteristics of original training data, due to which only classifying only using the generated data also helped. And then we perform BERT filtering, or filtering to choose the top quality samples, and we showed that filtering was helpful. Moving on to the final chapter, it's multi-corpus learning. We try to answer the research question: how to combine several available hate speech corpora to increase the total number of training samples. And our solution for this approach is, for this question, is multi-corpus learning. So multi-corpus learning, or we start off with multitask learning because that's the terminology used in the literature. So you try to combine several different data sets of different tasks together to jointly train a single model. And the aim of this is to improve the model generalization, where one task mutually benefits the other tasks, or mutually benefits from other tasks. So one example in real life scenario is uh, where a person jointly learns to play two or more musical instruments. The knowledge of music can be transferred from one instrument to the other. So it's just the instrument that changes, but the representation, that's knowledge, is quite similar and can easily be transferred. So we adapt the scenario of multitask learning to multi-corpus learning, because we use multiple corpora instead of different tasks. Here we treat one corpus as one task. So in a single corpus learning scenario, we have one data set which is processed by only one DNN model, or a set of corpus specific layers. Here, a model does not benefit from the availability of different corpus. However, what we try to propose is a multi-corpus learning approach. So in this this kind of model it's a single model, but consists of a shared layers and corpus specific layers. So the shared layers are the first few layers of the model, which processes data from all the corpora, thus benefits from the shared representation that has been learned from different corpora. And once the data is processed by the shared layers, the output of shared layers is passed through the corpus-specific layers for the particular task. For example, when we use dataset 1 or D1 as the input to the model, only the corpus-specific layers corresponding to the first, uh, corpus-specific layers of the first dataset is processed by the first set of corpus-specific layers. For our shared representation, we use the pre-trained BERT model as our shared layers. Excuse me. So moving on to the next setup, we look at fine-tuning the multi-corpus learning model. So in this, here initially when we perform multi-corpus learning, the shared layers, they look at all the data sets, but they're not fully optimized for one particular data set, because of which the performance over a particular data set might reduce, although the shared layers have benefited from the shared representation. So what we try to do is we take the model, multi-corpus learning, which is already trained, and then fine-tune over one particular data set on which we want to test. We call this as MCL fine-tune. So for example, if you want to fine-tune the model on the second data set, we take the model which was trained on all the available data sets, and and then we fine-tune on one particular data set, that's second data set. So now the shared layer and corpus specific layers are more optimized or more fine-tuned for a particular data set or the target data set. So we have tried to show the results of multi-corpus learning. So we have represented the average of 5 corpora, and the green bar indicates single corpora learning. The orange represents multi-corpora learning, and the red represents the model fine-tuned on a target corpora using multi-corpus learning approach. On the x-axis, we have macro average F1, the classification metric. And here is low resource scenarios. By 100, we mean we have used only 100 samples from a particular data set. So by 200, we have 200 samples from a particular data set. All training data indicates a scenario where all the available training data is considered. So as the first observation, we observe that fine-tuning the multi-corpus learning gives the best results among all the 3 approaches. With this, we can say that multi-corpus learning was not fully optimized in certain cases, leading to slightly lesser slightly lesser performance than the single corpora learning approach. And the second observation that we can make is multi-corpora learning alone, that's without an additional fine-tuning, gives significant improvements when the amount of training data is very low. That's when we have only 100 or 200 samples from a particular data set. Multi-corpus learning itself gives improvements. By this, we can say that with multi-corpus learning, we observe significant improvements in low resource scenarios. And even when we have all the available training data, or when the amount of samples are high, we can further fine-tune the multi-corpus learning to achieve better results than single corpora learning. We then look at domain adaptation. That by domain adaptation, here we mean supervised domain adaptation. And this has been performed using multi-corpus learning approach, or multi-corpus learning model has been used. So how do we do this? So when we have 5 corpora, we consider 4 out of 5 corpora. We use all the training data of these 4 corpora to train the multi-corpus learning model. So now the shared layer has benefited from the multi-corpora learning, or from all the data sets. We then take this model and adapt to a new data set. So the 5th corpora, which has been held out, we call it a target corpora. And this corpora is used to fine-tune the multi-corpus learning model. for which we add new set of corpus specific layer, which is specifically meant for the target corpora or newly added target corpora or the corpora to be fine-tuned, or the model corpora which is used to fine-tune the model, or for corpora used for the adaptation. And so now the shared layers which we obtain from the multi-corpus learning, as well as the task-specific layers which are newly added, are optimized for the new corpora or adapted to the new corpora. So coming to the results, average of 5 corpora are indicated. We have low resource scenarios where we have only 100 samples, 200 samples, 500 samples, or 1,000 samples for adaptation. And we have all the samples for adaptation. So at first, we see that single corpora learning gives, with all the data, we have macro average F1 of 73.2, and with domain adaptation, we have 74.7. So we can say domain adaptation was helpful. Further, when we look at low resource scenarios, when we have only 100 or 200 samples, there's a massive difference between the single corpora learning and domain adaptation using multi-corpora learning. So we have higher improvements when the amount of samples are lower. So by this, we can say domain adaptation gives better results than single corpora learning approach. So overall, we observed that corpus-specific fine-tuning of multi-corpus learning gives the best results. That's better than single corpora learning and multi-corpora learning. And multi-corpora learning gives better results than single corpora learning, especially in low resource scenarios. And domain adaptation using multi-corpora learning also gave better results than single corpus learning. Winding up with the conclusions. So we explored 3 different approaches to improve the deep learning based classification. And this has been done by increasing the amount of available training data. And to increase the amount of training data, we looked at 3 different methods, which answers 3 different research questions. So one is using semi-supervised learning, which combined the labeled and unlabeled data. And then we generated the new training data from the original training data using data augmentation. And then we combined different available hate speech corpora using multi-corpus learning. So for semi-supervised learning, we saw that transforming the representation space to consider the class label information was helpful. So by transforming the representations, we observed an improvements in semi-supervised learning, especially in low resource scenarios. And with data augmentation, we saw that the data which was generated by the conditional language model represented the original training data, because of which it helped in data augmentation and also showed an improvement in the performance with data augmentation. And then with multi-corpus learning, we saw that like combining several available hate speech corpora to train a multi-corpus model helped in enriching the representation of this model, which further helped in improving the classification performance. Overall, what we observed is, although the performance gains were very small by all the 3 methods, they were significantly high when the amount of samples were very few. So by which we can say all the 3 methods were helpful, but especially in the low resource scenarios. Future directions, what I foresee from the thesis, or what can we do for the future research. So first, so I'll first talk about the future research or the short-term research that can be pursued in each of these different approaches, and then we will discuss about the long-term directions. So first, semi-supervised learning. When a label propagation assigns a label, what we considered was sample with highest the highest probability for a particular class that label propagation assigned was the class label for a sample. So we considered 1:0 scenario, either either normal class or hate speech or abusive speech. Uh, it's like 1:0. But then we can look at the probabilities that is assigned. So whether it's 70% normal speech and 30% abusive speech. So these kind of probabilities can act as a confidence measure uh, to weigh the unlabeled samples uh, which have been labeled by label propagation. So by this we have the knowledge of which samples are uh, very close or strongly represents a particular class, and which samples do not, and we can consider this measure to improve the classification performance. And data augmentation, so diverse data generation. So when we generate the data, although it gener- so when we augment the data more, so with increase in the diversity of data, the information that goes into the classifier also improves. So this can help in improving the classification. So we need to look at uh, how we can improve more diverse data. Also, when we filtered the data, we observed that the data were uh, were taken from the centroid of particular classes. That's what we saw in the PCA plot. With this, we also observe a reduced diversity in the data that's considered for augmentation. So we need to look at how we can diversify the data that's used for augmentation. Alternate filtering strategy. For our filtering, we use the classifier. So a BERT model, which is fine-tuned on the original data, was used for classification. But then overall, we are looking at how to improve the classification performance. With this, it becomes a chicken and egg problem. We don't know how to which one to solve first, and thus we kind of have to look at a non-classification based filtering strategy as well. And adversarial learning. Uh, uh, for our approach, we have three independent modules. A module, the GPT-2 model, which is fine-tuned on the training data to generate the data. We then have a different module to filter the data. And then the third model, which is classification model to classify the data. And all these three models works independent of each other. But then adversarial learning is a way uh, where you can combine the generative model along with a discriminator to perform the classification. So the feedback from the discriminator or the classification model can be used as an input to the generative model so that better data can be generated. This is something which can be looked at in the future. And we looked at only one particular approach, that is conditional language model based augmentation for our data augmentation. We can look at different augmentation techniques, and also we can study the influence of combining them or combining different augmentation methods to improve the classification. And for multi-corpus learning, so in multi-corpus learning, we just so the model performance improves when the tasks are grouped together, or the tasks which are similar are grouped together. But in our scenario, we did not group any of the tasks, or we did not do an architecture search. So maybe looking at which tasks or which data sets are more similar and grouping them can be helpful. For our long-term directions, uh, we saw that hate speech, I mean, in challenges of hate speech, we know hate speech depends on the context. And with advances in research, and we also know that there are different types of context. For example, a hate comment can be associated with an image, where image is in context. Such context details, which can which can even be multimodal, can be incorporated uh, as features for hate speech classifier. And the next thing is annotator's confidence or annotation noise. So when the data is annotated, few of the data sets provide details on how many annotators have annotated, and or so what is the number of annotators who have voted for a particular class. With this, we can try to estimate the noise in the annotation, and these annotation noise or annotation confidence measures can be uh, used as features for hate speech classifier. And then the explainability. So although we looked at uh, a model performing classification, this classification into normal speech, abusive speech, or hate speech, we did not look at why a model calls it a normal speech or abusive speech, or why it labels as a particular class. So maybe looking at them gives more insights and also more understanding of the phenomena of hate speech itself. These are my publications in my PhD. The last one is a preprint which we have submitted to the upcoming TST conference. And thank you. That's it from my side.
Thank you.
And feel free to ask any questions, and I'll answer.
Yeah, of course. We do have questions here. Igor Gribkov asks, taxi classifiers are known to easily overfit for certain keywords, such as lesbian, gay, Syrian, and produce predictions according to the label distribution in the original data. Were the test datasets somehow balanced with respect to identities mentioned in the text, gender, race, sexual orientation, to capture such model biases in metrics?
In my case, no, the test sets were not balanced with respect to identities such as gender, race, or sexual orientation. I haven't done that. But then there are a couple of studies that have shown this. So they do not balance in the test set, but they balance in the training set. So this is to remove the bias in the data set. So one of the problems that I mentioned, the question really corresponds to the problems here, biases in the data set. So based on sampling strategy, for example, when the authors or the researchers are focusing on, let's say, obtaining hate speech data set which shows sexism, they use identity words that represents the women as target, simple slur as bitch, lesbian, or whatever. So with this, a lot of samples coming from particular data set have these kind of terms, and they don't generalize well on the test set. So instead, what the researchers who focus on balancing or debiasing the data set do is they take the sentences and replace with the alternate terms. For example, if you want to remove the bias towards women gender, you replace the women identity term with the masculine identity term. That's, for example, if you say this guy is the biggest, this girl is the biggest lesbian, you change it to this boy is the biggest gay. So the data set now has, the original training data set has both identity towards women and men. With this, you can improve the generalization. So that's what has been done in the literature, and I haven't looked at it. Yeah.
Okay.
Maybe I can add something.
Sure.
Hello, everybody. So the goal of Ashwin thesis, it was to use some automatic methods to detect the hate speech and to try to generate new data, or to use label propagation to have more training data. So it was the problem of bias in the corpora was no problem for Ashwin. But in our multi-speech team, we have another thesis of Tulika Bose, and she worked in this problem, the problem of bias in the data sets, and how to take it into account in several, using several methodologies. And Tulika will defend his thesis in about 5 or 6 months. So if you want, she can present to you his thesis in 4 or 5 months.
Yeah, that would be great. Thank you.
Yes.
But what I think is interesting is interplay between the question of bias in the data set and the augmentation techniques that have been considered here. So, because the bias in the data set more or less naturally should produce the bias in the augmentation set.
Yes.
Yes, of course. Yes. But
And,
maybe, yes, maybe it can be a new subject for a new thesis.
Okay. Now we have yet another question in chat. Pavel asks, have you checked the correlation of hate speech with people economic level? Cultural level could be even better indicated, but even harder to estimate. Economic data could be obtained from surveys.
No, from this. So one thing with this is from the perspective of my thesis, we really haven't focused on the key elements. Yes, in fact, like this project was done in collaboration with the social science people. We have collaborations of 4 universities. 2 of us are focusing on social science, and 2 of us are focusing on computer science. With computer science perspective, we just looked at the classifications, but not really the influence of hate speech or the where hate speech is occurring, or so we did not look at these aspects. So this was not within the scope of the computer science, but a similar study has been is being done by the social science collaborators of our project.
All right, thank you. I have a question. You have considered 2 approaches to multi-corporal learning. One that's just like straightforward multi-corporal learning, and the other is domain adaptation multi-corporal learning. And you have mentioned that both are better than single corporal learning, but no comparison was done between these 2 multi-corporal learning approaches. What could you say about that?
Sorry, I might have lost your question partially. Can you?
Yeah, of course. Now further multi-corporal learning, like just a little bit further, and yet a little bit further, and yet a little bit further. Sorry. Well, the final result. Yeah.
Yes.
So multi-corporal learning has better performance than single corporal learning. That's more or less obvious. Now you consider the other approach to multi-corporal learning. That's the domain adaptation multi-corporal learning.
Yes.
You show that domain adaptation multi-corporal learning is better than single corpus learning.
Yeah.
But you don't compare the normal multi-corporal learning with domain adaptation multi-corporal learning.
Yes. So one difference with domain adaptation, I would say, is I have the results in an appendix. Okay, not here. Okay, sorry about that. Going back to the slides. So with domain adaptation, what we try to look at is, so what happens in multi-corporal learning is, if we have 5 corpus, the shared layers have already seen the data from all the 5 corpus. Okay, let me put forward this scenario. We had 5 data sets, 4 of them coming from Twitter and 1 from Wikipedia. Okay, so now if you're looking at fine-tuning on Wikipedia dataset, whether it's multi-corpus learning or multi-corpus learning fine-tune. So if we have used Wikipedia data here and further fine-tune our shared layers or multi-corpus learning model, this shared layers have already seen the Wikipedia dataset. It's just that we are better optimizing it. But if we move on to the domain adaptation where we have used Wikipedia dataset. So if you look at the first approach where we learn multi-corpus learning model, these models have been trained only on the Twitter data set, and they haven't looked at the Wikipedia data set at all. But then we fine tune on Wikipedia data set. So the main objective is to the main objective here is to see whether the knowledge or representation of hate transfers. And sorry about just going with the average results, but one of our experiments which where we have looked at the model trained only on the Twitter data but adapted to the Wikipedia data set, it performed much better than the single corporal learning approach. So yes, there is no comparison with uh, the model performance on the original multi-corporal learning and multi-corporal learning with domain adaptation. But yes, so the research question that we were trying to answer was different, but your question really does make sense, and I think we need to look at comparison from that perspective. Normal multi-corporal learning versus domain adaptation multi-corporal learning as well.
Yeah, thank you. And I think the question is well related to the neural network architecture,
yes.
Meaning that you can consider domain adaptation not only on the, like, you can build corpus specific layer on the top on the classifier.
Yes.
But you can build domain corpus specific layers on the bottom, on the embedding.
Yes, right. Yeah.
You can do this bottom layer adaptation, you can build top layer adaptation, or you can do both. And
yes.
And that can be considered on drop one approach as you do for domain adaptation, both for the like normal multi-corpus learning you have considered and for the domain adaptation, meaning that I'd say more architecturally accurate would be considered apples to apples comparison, where you have like 4 data sets on in like learning stage and the 5th data set in the domain adaptation stage, but you can work either with bottom layers or with top layers or both. Not sure that it would bring like very significant results, but it looks like it might be a little bit more accurate.
Yeah.
Just give it a little bit of thought.
Yeah.
Okay, we have yet another question. Okay, Pavel continues to ask his questions. I mean, from statistics perspective, have you tried to use Twitter accounts / people as a variable to find a propensity for individuals to use hate speech?
No, not really. With the corpus that we have, we really did not, I mean, there was no details on the author of the comments. There were no details on the author of comments, and neither we tried to sample the author details. So authors were not used as features. But from my understanding on the knowledge on the existing literature, this has been partially done. So for example, one of the data set, Davidson, that we have used, the author himself has done a bit of author profiling, and there are a few other related works as well. They say that when they have used, so it basically depends on the sampling bias again. For example, this particular data set, Davidson, about, I think 90% of the racist comments or sexist comments came from just 2 authors. So what they try to show, also a couple of works try to show is these models, they don't just learn in this kind of bias data sets, they don't just learn the the notion of hate, but they learn the the way or the style of authors, and the classification is rather biased to the author styles and not really, uh, not 100% towards the notion of hate, but also to the author style as well. Uh, and also a couple of works which is faintly related to my thesis. What they have tried to do is they have tried to obtain the author details uh, and created, so they have used graph-based approach or graph embedding approaches to learn the representation to see where the hate is coming from. Uh, so this kind of works have been done, but it's not really uh, done in, looked at in my thesis.
Okay, thank you. Anybody else? Any more questions? Okay, it looks like we don't have any more questions. Ashwin, thank you for your presentation. Irina, thank you for your help here.
Thanks a lot, Nick. Thanks for this opportunity to present my work, and thanks a lot for the questions. The questions were rather insightful and probably open more research directions, I would say.
Thank you, and have a great day, everyone, or any other type of time.
Thank you. If there are any questions, please free to drop me an email. Thank you.
Yes, no problem. Thank you, everybody. Thank you.
Thank you.
Bye.